Every time you navigate to a website, your machine fires off a query to map the domain name to a numerical IP address. That request leaves your local network as a data packet, traveling across the public internet, where it can be intercepted and inspected by on-path nodes. This exposes a core vulnerability in internet architecture. Traditional DNS operates over port 53 and transmits both the target domain, the queue name, and your source IP address in completely unencrypted clear text. Anyone sitting on the network path, from your local ISP to a malicious actor, can read exactly where you are trying to go. To understand how engineers are working to secure this process, we first have to deconstruct the protocol itself. We will start by mapping the distinction between the logical domains you type into your browser and the administrative zones that actually route your request. From there, we will examine the physical payload constraints of the User Datagram Protocol, or UDP, and why extended DNS is necessary to carry modern cryptographic signatures. Finally, we will analyze the precise architectural trade-offs between two competing security standards, DNS over TLS and DNS over HTTPS. Retrofitting encryption onto a globally distributed protocol designed 4 decades ago requires navigating strict structural limits. Doing this successfully means applying heavy cryptographic layers without breaking the internet's highly efficient routing logic. The DNS namespace is a strict hierarchy, cascading from a single root node to top-level domains and subdomains. Operationally, this tree fractures into distinct administrative territories called zones. A zone can encompass multiple subdomains or be explicitly delegated to external servers. The machines responsible for these specific zones are authoritative name servers. They hold the definitive DNS resource records for their designated territory without guessing or searching. A primary name server loads its zone contents directly from a local configuration database maintained by the domain administrator. As this schematic illustrates, secondary name servers provide necessary network redundancy. They stay synchronized by fetching exact copies of the zone data directly from the primary server in a process called a zone transfer. While domain names represent the readable map of the internet, zones dictate physical routing and define the true administrative boundaries of power. This diagram traces a typical resolution request. A client queries a local recursive server, which acts as an intermediary, navigating the hierarchy of zones to track down the authoritative server that definitively owns and supplies the zone data. To prevent millions of users from querying the global root server simultaneously, operating systems and recursive resolvers temporarily hold on to the answers they fetch. This caching layer is the internet's primary method for reducing latency. Every DNS record includes a time to live, or TTL, countdown. Assigned by the authoritative server, it determines exactly how many seconds a cached record remains valid. When the TTL countdown hits 0, the record expires. The caching server deletes it from local memory, forcing the system to execute a full recursive fetch back to the authoritative server the next time that specific domain is requested. Without rigorous validation, an attacker can execute cache poisoning. They feed false IP data into the decentralized cache, silently routing users to malicious servers. Aggressive caching prevents global infrastructure from collapsing under continuous queries. However, this highly decentralized landscape allows stale or poisoned data to easily disrupt user connections. Legacy DNS operates over the User Datagram Protocol, which historically capped payloads at exactly 512 bytes. However, modern internet security broke this limit. Cryptographic signatures through DNSSEC and larger IPv6 addresses generate resource records that easily exceed this fixed capacity. To solve this, Extended DNS, or eDNS0, uses an OPT resource record to negotiate a larger UDP payload size. With eDNS, the theoretical buffer dynamically expands up to 64 kilobytes, accommodating the dense cryptographic data without issue. Massive UDP packets face IP fragmentation. Exceeding a router's capacity slices them into smaller pieces, significantly increasing the risk of complete data loss. To prevent fragmentation, network administrators will artificially limit eDNS buffers to a safe size. If the requested data still overflows that newly constrained limit, the server marks the response as truncated, forcing the client to retry the request over a slower, connection-oriented TCP link. The evolution of DNS continuously pushes against the limits of lightweight UDP. When data grows too heavy, network reality forces a structural fallback to TCP. Returning to the vulnerability of clear text routing, the modern solution requires encrypting queries in transit. This relies on the TLS handshake, exchanging keys to form a secure cryptographic session. The first standard is DNS over TLS, or DOT. It encapsulates standard DNS data directly inside a secure TLS tunnel. DOT routes this encrypted traffic through a dedicated port 853, making the presence of DNS traffic unreadable, yet highly visible and easily identifiable. Because TLS handshakes introduce delay, DOT utilizes pipelining. Clients can resolve multiple queries over a single persistent session, offsetting the initial latency penalty. The alternative standard is DNS over HTTPS, or DOTCH. The query is formatted as an HTTP request before TLS encryption is applied. Routing through standard port 443 perfectly camouflages the DNS query within massive streams of regular HTTPS web traffic, making it completely indistinguishable. The choice between DOT and DOH forces a fundamental conflict between institutional network oversight and the absolute privacy of the end user. In an enterprise environment, DOT is the optimal protocol. Organizations that mandate strict network visibility to implement malware protection or parental controls rely on port 853 to identify and monitor DNS activity. Conversely, DOH is the protocol of choice for end users seeking privacy. By hiding queries in standard web traffic, DOH bypasses DNS-level censorship, completely blinding local ISPs and network administrators to the user's intent. Both protocols share a structural penalty. Because they rely on the TCP transport layer and mandate heavy TLS handshakes, both DOT and DOH incur significant latency degradation compared to the unencrypted UDP baseline. To resolve this latency bottleneck, the Internet Engineering Task Force proposed RFC 9250, establishing a new standard, DNS over QUIC. To fix this, the QUIC protocol integrates TLS 1.3 encryption directly into the highly efficient, connectionless UDP transport layer. Because it operates over UDP, DNS over QUIC eliminates the head-of-line blocking issues inherent to TCP. It recaptures the raw speed of legacy DNS while maintaining complete cryptographic integrity. The 4-decade evolution of the domain name system proves that securing the Internet's core infrastructure is a constant, delicate balancing act. It requires navigating the friction between raw network speed, absolute privacy, and structural stability.